Now, at the end of the previous video, we described 4 properties of dot product. Symmetric, doesn't matter which order you do the dot product, get the same result. Distributive, I can dot a sum of vectors and that's the sum of the dot products. Bilinear, which in fact generalizes distributive. Not only can I dot a sum of vectors, but I can dot a linear combination of vectors and get the linear combination of the dot products. And I can do that on either side. And positive definite. The dot product of a vector with itself is always bigger than or equal to 0, and it's only equal to 0 when u is the 0 vector. Now these 4 properties could be applied to other operations. In fact, there are other operations that we're not going to get into right now that satisfy these 4 properties. And these are also called, well, they're not called dot products, they're called inner products. And the neat thing is that if I can define the inner product, I can also define a length and an angle. Remember, we defined length as the square root of the dot product. And we defined angle as the dot product divided by the product of the lengths of the vectors. So once we have a dot product, we can define length and angle. And it turns out that once we have any binary operation like this that involves 2 arguments that satisfies these 4 properties, we can define a length and an angle. All right. Now we have an example here of the so-called Lorentzian inner product, which is not quite an inner product according to the previous definition because it's not positive definite. In this case, we have the inner product of 2 vectors, and these vectors have to be 4-dimensional, right? And the inner product of 2 vectors is the first component times first component plus second component times second component plus third component times third component minus fourth component times fourth component. Now, why minus the last component? Well, you'll have to ask Einstein about that. But physically, this is interpreted as 3 space dimensions and 1 time dimension. Time is treated differently from space, right? So that's kind of the key to Einstein's space-time. Space-time is 4 dimensions, but the time dimension has a little bit different properties than the space dimensions, right? So if we have coordinates x, y, z, and t corresponding to 3 space coordinates and time, then the length of a vector defined using this inner product is the dot product of x, y, z, t with itself, which is going to be x times x because x is the first component, plus y times y because y is the second component, plus z times z, z is the third component, minus t times t because t is the fourth component. So x squared plus y squared plus z squared minus t squared. So it's possible for the inner product to be 0. For instance, if x is 1, y is 0, z is 0, t is 1, then you get 0 as the length of the vector. Right. So here we have 2 types of lengths. We can have, well, 3 types of lengths. We can have positive lengths, 0 lengths, and negative lengths. And those have physical interpretations. It has something to do with a property called causality. So we get into physics. This is fascinating stuff, but we don't have the time and space to go there right now. So let's move on. Now, we were talking about how you can define angle in terms of inner product. So here we're using this notation with the angle brackets instead of the dot product, but you can just think of this angle brackets as dot product because that's the example that we've looked at so far. Now look at this thing on the left-hand side. This is actually how we've defined cosine. Go back and see. When we define cosine, a little bit farther, back here on page 90, okay, look at this. To define the angle, you use this relationship, and you have to use this relationship to solve for cosine theta. Cos theta is just equal to u dot v over length of u times length of v. So we've down here is the same thing. We're just writing u dot v as angle brackets u and v. Now you know that the cosine of any angle has to be between -1 and 1. So in particular, its absolute value must be less than or equal to 1. All right? So if we really want this quantity to make sense to define a cosine, we need to guarantee that this quantity is less than or equal to 1. Right? So this proof kind of involves, it amounts to a consistency check that defining cosine in this way makes sense, that we do end up with a number between -1 and 1. Right? Now the proof of this inequality is very clever, and it involves kind of a trick. So we know that inner product is positive definite. So in other words, if I take an inner product of a vector with itself, it's always greater than or equal to 0. It's only equal to 0 if the two vectors involved are 0. Right? And then we use the bilinear property to expand this out. Right? Because we know that we can distribute this vector over these two vectors, and then we can distribute again. So if you expand this entire thing out, you're going to get basically the FOIL expression. You get u times u plus the two cross terms. There's u with v and v with u. So that's going to give you two terms here. And then you're going to have the AV with the AV gives you a squared VV. All right? So we know that this is true according to the definition of inner product. This must be true, that the inner product of a vector with itself must be greater than or equal to 0. So here we have a quadratic in the unknown alpha, and that must be greater than or equal to 0 for any value of alpha. Okay, so we have that this function must be greater than or equal to 0 for any alpha. Let's simplify our notation a little bit. This is a quadratic in alpha, so let's call the constant term c, and we'll call this coefficient of alpha here, we'll call that 2b, and then the coefficient of alpha squared, we'll call it a. So we write this quadratic as a alpha squared plus 2b alpha plus c. Same quadratic, just reverse the order of the terms. All right, and we know that a alpha squared plus 2b alpha plus c must be greater than or equal to 0. Okay, so that's what we have here. Let's zoom in here. Okay. All right, so in particular, it's also true that the minimum over alpha of a alpha squared plus 2b alpha plus c is equal to 0. It must be greater. That's greater than or equal to 0. It must be greater than or equal to 0. Okay, how do you find the minimum over alpha? So the minimum, to find the minimum, well, you may remember from calculus that to find the minimum, you take the derivative of this and set it equal to 0. Now, if you do that, take the derivative here, that's going to give you 2a alpha. And then here we have plus 2b equals 0. And you can solve that for alpha. Take the 2b to the other side and divide, and you're going to get alpha equals minus b over a. So I need to plug this into my expression. When alpha equals minus b over a, then this quadratic takes its minimum value. Okay, so I'm going to plug that in. So I'm going to have the minimum value is going to be a, and my alpha is minus b over a squared plus 2b minus b over a plus c. Okay, and that must be greater than or equal to 0. Okay, because this is the minimum value. Okay. All right, now I can simplify this. This is actually b squared over a squared, but the a cancels one of those. And this is minus 2b squared over a squared. Minus 2b over b squared over a. So these can be combined together into a minus b squared over a. So we get minus b squared over a plus c is greater than or equal to 0. We solve for this. This is c is greater than or equal to b squared over a, like that. Did I do that right? So now we want to substitute. What is my value of c? Well, c was equal to uu. we have UU here. What's my B? Well, B was equal to, you can go back and check this, is UV. And A was VV. Okay. All right. So we can divide both sides by UU, which we know is a positive as long as U is not 0. So that means that 1, this should be greater than or equal to, sorry. So 1 is greater than or equal to UV squared over UU and V times VV. Okay. So pretty cool. You take the square root of this, and you get what's known as the Cauchy-Schwarz inequality, which was what we wanted to prove here. All right. So again, the point of proving this is to show that we can use this relationship to define cosine of an angle. All right. Now, one more mathematical fact we want to prove concerning inner products is expressed in this diagram here. Remember, what we're using inner product to define a notion of length. And if you have two vectors in a relation like this, you have the length of u should be the length of this line. Length of v should be the length of this line. And u plus v, we know that the vectors are added head to tail like this. So u plus v is the third side of a triangle whose other two sides are formed by vector u and vector v. Now you know that the length of this side can't possibly be bigger than the sum of these two sides. In other words, using this notation, the length of u plus v should be less than or equal to the length of u plus the length of v. Now, we know this is true in 2 dimensions. We know this is true in 3 dimensions. But can we guarantee this is true when we define length in terms of inner product? And in fact, we can. We can go up here. And so this is called the triangle inequality for obvious reasons, because we get it from a triangle, that the length of u plus v should be less than or equal to the length of u plus the length of v. And the proof is a little bit more straightforward than the Cauchy-Schwarz inequality. We express the length of u plus v squared is, in fact, is defined as u plus v dot u plus v. Right? And then we work this out using our distributivity of the dot product, and we get 3 terms. And we saw this before. U dot v is how we define the length of u squared. V dot v is how we define the length of v squared. And then this is how we define cosine of theta, right? And so we happen to know, and we prove in the Cauchy-Schwarz inequality, that cosine theta actually will always be less than or equal to, will be between -1 and 1, so it'll have absolute value less than or equal to 1. All right, so let's see. So we've done a little trick here. Instead of u squared plus v squared, we replaced it by u plus v squared. Now, is that equal to each other? And the answer is no. If I square this out, I get u squared plus v squared, plus I get a cross term. The cross term is what? The cross term is 2 times this number times this number. So the cross term is 2 times u times v. So these two terms is not equal to this. There's another term, 2 times u times v. So in order to make this an equality, I'll have to subtract out 2 times u times v. And that's where this -1 comes from. But this -1 times 2 times length of u times length of v cancels out the extra term I've introduced here by making this a square of the sum of terms. All right? Now, what about this? Well, cosine of theta must always be less than 1. All right? This is always positive. This is always positive. So this term here is negative. Right? So the sum of these terms must be less than or equal to this term by itself. All right? So we can drop out this term. If we drop out this term, we get a less than or equal to. Okay? Because this term only makes this expression smaller. All right? And then here we have we take the square root of both sides, take the positive square root of both sides, and we get this result. All right? So we've got our triangle inequality. We've got our picture. Here's an example where it shows that it's true. And I think that's the end of this section.